So let's pause for a second and think about how we've been finding the dot product so far. We've been using this formula, which is the magnitude of the one vector times the magnitude of the other vector times the cosine of the angle between them. But that only works if we can sort of figure out the angle between them, or at the very least, figure out the cosine of the angle between them and make it run that way. Okay, well, that's all well and good, but what if it's in 3 dimensions? What if the angle between them is a little bit more complicated? What if we don't know the angle? So we want to be able to come up with a method that will work even if we don't know the angle. All right, so we're going to use our handy dandy law of cosines that we learned in pre-calculus and trigonometry, which tells us that a squared is equal to b squared plus c squared minus 2bc times the cosine of a. Now, how does this relate? Well, suppose the sides of that triangle were made up with vectors. So we have a vector v right here, which is v1 and v2, and a vector u, which is u1 and u2. So this side over here, which is the equivalent of a, is vector u minus vector v, which would be u1 minus v1 and u2 minus v2. All right, so now if we think of these as being a, b, and c from the triangle, then we can say with substitution that a, which is u minus v, and its magnitude squared, will be equal to b squared, which is the magnitude of u squared, plus c, which is the magnitude of v squared, minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between them, which in our case is theta. Now this piece over here should be setting off little bells in our head, because that's the definition of the dot product of u and v. So we're actually going to solve this equation for this piece. All right, but first we have some more work to do. Now the magnitude of a vector is the square root of the components. So in this case it'd be u1 minus v1 squared plus u2 minus v2 squared. And we're going to take that magnitude and we're going to square it. And that is equal to the magnitude of u, which is the square root of u1 squared plus u2 squared. And we're going to square that square root, plus the magnitude of v, which is the square root of v1 plus v2 squared, minus 2, and then the dot product of u and v. And again, this is the piece we're actually going to solve for. Now it looks worse than it is, because you have to remember that when you take a square root and you square it, it all goes away. And you're left with u1 minus v1 squared plus u2 minus v2 squared equals u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2 u v, dot product of u and v. Now these two are binomials squared, so you have to FOIL them. You have to distribute. Sorry, I just realized my paper behind was kind of showing through. So that's u1 squared minus 2u1 v1 plus v1 squared. First, outers, inners, last. Plus, then you have to do it again for this one, u2 squared minus 2u2 v2 plus v2 squared equals, and then all the stuff on the right side, u1 squared plus u2 squared plus v1 squared plus v2 squared minus 2u v dot product. Oh my goodness, it looks so horrible. Yes, but realize both sides have a u1 squared. So you can subtract u1 squared from both sides and it's gone. Both sides have a u2 squared. So you can subtract u2 squared, gone. Both sides have a v1 squared. Both sides have a v2 squared. So you can subtract those pieces, gone, gone, gone. So the only thing left is minus 2u1v1 minus 2u2v2. And that's equal to negative 2 and the dot product of u and v. So if I want to solve for this, I just want to divide by negative 2. And if I do it over there, I have to do it over here. The negative 2 cancels with both of those, and you're left with u1v1 plus u2v2 is equal to the dot product of u and v. Now notice there's no theta required, right? There's no theta anywhere in the problem. And this means we have a new way to find dot products, and quite frankly, an easier way. So if you want the dot product of u and v, you take the x components plus the y components. And that's it. Done. And if it's in 3 dimensions, it's the same thing. It's just you expand it to the 3rd dimension. So it'll be u1v1 plus u2v2 plus u3v3. And there we have it. Easier formulas to use that don't require the angle. Now that said, will we always use these alternative formulas? No. It depends on the problem. We're going to see applications where we know the angle, right? And then we're going to see applications where we don't. So when we do not know the angle, this method can be used. So let's do a little example with that. Right here for example 2. So we're going to find the dot product of each of the following pairs of vectors. So we have negative 4i plus 9j and 3i plus j. So notice they both are the same type. So these are i's and these are j's. So this is going to work out beautifully. So a dot product with b would be the I components, the x components. So negative 4 times 3 plus 9 times 1. And that would be negative 12 plus 9, which would be negative 3. And indeed, we are getting a scalar result, which is what we expect. Dot products should lead to a scalar. They should lead to a number. All right, let's practice it with 3 dimensions. The v dot product with the w. And by the way, this is commutative. It doesn't really matter what order I go in. So that's 4 times negative 5 plus 4 times 1 plus negative 2 times negative 8, which is negative 12 plus 4 plus 16. Oh, sorry, negative 20. Good grief. I didn't read my own handwriting. That's a 5, not a 3. So negative 20 plus 4 plus 16. There we go, which is 0. Ooh. Now let's remind ourselves that when that happens, when we have a dot product and it is 0, that means that those 2 vectors were orthogonal. Again, orthogonal is the 3-dimensional version of perpendicular. Right? Perpendicular doesn't really make sense in 3 dimensions. It's that idea, though. All right, so let's make a note. V and W are orthogonal. All right, now this last one's a little tricky because it's easy to look at it and go, oh, 2 times 3 and 7 times 6, but no, no, no. They're in different placements. If you look, the R is actually 0 because there's no I component, 3, 7. And the T vector is 2 in the I component, negative 6, 0. So when we multiply, or do the dot product, I should say, then we would take 0 times 2, because there's no I component, so 0 times 2 plus 3 times negative 6 plus 7 times 0, which ends up being negative 18. When they write them in that form, it's easy to miss that some of them exist and some of them don't, so be careful with that.